So in the last class, we had started on SCRs and we had also started looking at how to analyze the device. As I told you, SCRs basically are 4-layer devices. So I'm going to have PN, PN. This is the way it is going to be. So which I said can be looked upon as a PNP transistor. So this is a PNP transistor which is connected to an NPN transistor. So if I say that this is P, this is N and this is P and this is going to be N, P, N, this particular P is connected to this P like this, and similarly this N is connected to this N like this, and we said that this is anode, this is cathode and this is the gate terminal, right? So this is the way we are going to visualize an SCR, which is a 4-layer device basically. So if we are looking at these two transistors, when I am applying positive to anode and negative to cathode, right? You can see that this transistor, we have, this is the emitter. So emitter base junction is forward biased. Similarly here also emitter base junction is forward biased. N is negative and P is not having any potential as such. So both these will be forward biased, but if you look at the N of the collector here, either this or this, that particular junction is reverse biased because we are not applying any voltage at all. So they are going to be essentially reverse biased. So if I apply a positive voltage here to the gate with respect to cathode, then what is going to happen is I am pushing a gate current here. So if I am pushing a gate current here, I am going to have a larger collector current as per the transistor operation, because beta times IB, beta is the amplification factor, current amplification factor. So I am going to have a large current flowing through the collector. So that is going to flow into the base of the other transistor, because of which again I am going to have a larger collector current here. So it is essentially feeding into each other, and even for a very, very small amount of gate bias, we are going to see that eventually both the transistors are driven into saturation. Both of them are conducting with very, very minimal voltage drop across themselves. That's what we mean by saturation. So once I just give a pulse, I have already started the conduction process, because of which if I remove the gate pulse, no difference will it make to the device. So the device will be latched into conduction and I don't have to do anything to keep it still in conduction mode. So this can be visualized as a positive point or a negative point, because if I give a gate pulse and if it is latched into conduction, well and good, I don't have to give any gate signal at all. So my gate signals, circuits, method, whatever is the functionality, that is minimized. No problem at all. I will not have any losses and so on and so forth. But if I want to turn it off, it is not going to be easy. If I am, for example, talking about an inverter, I had shown this inverter earlier also when I was talking about RL load and feedback diode. So this is an inverter circuit with a DC voltage as the input and AC voltage as the output. So this is going to be my inverter circuit. So if I say that this 1 and 1 dash correspond to positive half cycle when the current is flowing in this direction. Okay, if I have 1 and 1 dash turned on, the current is going to flow in a particular direction. If I am going to have 2 and 2 dash turned on, 2 and 2 dash turned on, I am going to have the current in the opposite direction with 2 and 2 dash turned on, whereas this is going to be for 1 and 1 dash turned on, right? But By chance, if I am not able to turn off 1 and 1 dash, if I am not able to turn off 1 and 1 dash, but I have turned on 2 and 2 dash inadvertently, without knowing, then what will happen is, both these will conduct together, both these will conduct together. So you are looking at a dead short circuit across the DC supply. So extremely large currents are going to flow in case I am not able to turn off 1 and 1 dash and I have turned on 2 and 2 dash. That kind of a condition is generally known as shoot through. In an inverter, we call that condition as shoot through, in which case I am essentially going to have, a short circuit right across the supply. So this condition is definitely a very dangerous condition because the battery is essentially like an infinite source. So it will be able to circulate a very, very large current, and if these devices are not able to withstand that current, they are going to conk out. So if I have 1 and 1 dash and 2 and 2 dash as thyristors, they are all SCRs or thyristors, then I'm not going to be able to turn them off very easily. So whenever I have to use a thyristor in a DC circuit with the input as DC, I have to have some additional circuits to make sure that they are turned off well in time. Whenever I want to turn them off, I have to use this additional circuitry to make sure that they are turned off well in time. Those additional circuitry which are meant for turning off the thyristors or SCRs, these are generally known as commutation circuits. Commutation basically stands for current transfer. So I'm going to transfer the current from one set of devices to the other set of devices. So I call these circuits which are able to turn off one set of devices and transfer the current over to another set of devices, I call them as commutation circuit. Right? So if I look at actually the types of thyristors or SCRs, there are mainly 3 types of SCRs that are available in the market. The first and foremost one, we call them as power frequency thyristor or converter grade thyristor. Converter grade thyristor is generally used for rectification. It is used for rectification. So converter and rectifier again are used interchangeably. They are kind of synonymous. So converter grade thyristors are generally used for rectifier operation, whereas there are inverter grade thyristors. Inverter grade thyristors are generally used in those circuits where I may do DC to AC conversion. So depending upon how quickly I am going to turn on or turn off the devices, I am going to get the frequency output modified accordingly. If I do 1 1 dash and 2 2 dash alternately turning on very quickly, then the frequency of the output AC will be large. If I am doing it slowly, the frequency of the output AC will be small. So if I want to go for higher and higher frequencies, then the normal converter grade thyristors, which are normally slow, they are much slower. Turning on and turning off takes a longer time. So inverter grade thyristors can be used in those places. So these will be faster normally, whereas this will be generally slower. What I mean is turn on and turn off. This will be generally pretty slow for the converter grade thyristor, whereas it will be fast for the inverter grade thyristor. And normally we give a gate current in any of these devices to turn on. Sometimes we may use light to activate, so that photoelectric effect kind of thing we will use, and that will emit some electrons, because of which I will have the conduction possible. So the third one is LASER. LASER is light activated silicon controlled rectifier. So LASCR is, those devices will be activated basically by light. So these are light activated SCRs. So these are mainly the three types of devices that are available in the market if you go under the category of SCR. So if you actually look at the ratings, SCR ratings are really large that are available in the market, are very, very large. In fact, there are some companies, in fact our BHEL produces some SCRs, in Mitsubishi produces, Fuji, Toshiba, Infineon Technologies, all these things, International Rectifiers in USA, all these things produce, SCRs. And Mitsubishi generally has a very, very high rating, so also is Infineon. Mitsubishi rating is of the order of about 6.5 to 8 kilovolts along with about 4 to 5 kiloamperes. Very, very large rated SCRs are available from Mitsubishi. But mostly the highest grade SCR, highest power rated SCR will be converter grade. Inverter grade, because they have to be turned on and turned off very quickly, which means huge number of charge carriers, they have to be swept out. It takes longer. So generally inverter grade thyristors will be available only at lower rating. This may be available only at lower rating, whereas this will be available at higher ratings. So these are, some of the characteristics of thyristors when we look at the different types. Now let us try to take a look at how to fire a thyristor or how to trigger a thyristor. How are we going to trigger an SCR? What we mean by triggering or firing is, we are going to turn it on from off condition, it is going to be pushed into on condition. That's what we are trying to do. So invariably, thyristor, by the way, the symbol is somewhat like this. I'm going to have anode here, cathode here, and gate terminal is generally specified like this. So to this gate, I'll have to give a small amount of positive bias. Then it would be able to conduct, right? But if I look at the current amplification in this case, Ig versus I anode, if I try to look at it, generally in an SCR it is 1:1000 or more. So if it is like a 1000 ampere thyristor, 1 ampere of current would do in the gate for it to be triggered. So obviously the circuit that is connected here is going to be microelectronic circuit, whereas what is connected here will be power electronic circuit or high power circuit. So as I told you earlier, it is essential for us to have isolation between microelectronic circuit and power electronic circuit, because if something goes wrong in the power side, huge amount of current will flow into electronic side and it will not be able to withstand. So normally the grounds will be isolated. The grounds will not be connected together. So how do we really, isolate the ground of the SCR's gate versus anode? That's what we'll have to check. So let us say I have probably gotten some pulse. Something like this. This is the pulse that I want to give it to the thyristor. Okay? If I give a pulse directly, and if I am planning to use a transformer for isolation, then the transformer will saturate. Transformer is not supposed to carry DC. So if I am trying to isolate the gate circuit with that of anode circuit with the help of a transformer, I would like to convert this pulse into, some kind of smaller duration pulses. So what we can think of is like a clock in your computer or microprocessor. I can have a clock and this high frequency pulse and the normal pulse. Both of them can be given to an AND circuit, AND gate. So if I do that, whenever I'm going to have this pulse, I'm going to get essentially the output of this to be, all here it will be 0, and then I'm going to have some pulses like this. This is how the pulses will be, right? This will be the output of the high frequency ANDed circuits. So this now, if I can give it to a transformer, in all probability the transformer will not saturate provided I give ample time here for defluxing, or whatever is the flux that has been accumulated in the transformer winding, it should have enough sufficient time to kind of, get rid of that flux, right? So this particular thing, whatever is the high frequency, so this is HF pulses and this is HF ANDed pulses. So high frequency ANDed pulse, now this may be only of 5 volts and a few microamperes in all probability. If it is a 1000 ampere thyristor, I said that I will need 1 ampere to fire it. So I need to amplify it. So there has to be a current amplification circuit in between. So whatever is the output here, this goes to current amplification stage. So the current amplification stage can be a simple common emitter amplifier, like what you have seen in transistor. Maybe you studied this in 12th class. After that, I don't know whether you guys have again studied transistor. ELL 100 little bit was introduced to you in the form of transistor, but we will have to have a current amplification stage. So this current amplification stage normally will be an NPN transistor. So whatever is this signal, this we are going to give it to the gate, and here is my transistor. So I can imagine as though the transformer is here, right? The transformer primary I have shown, and I necessarily have to have another secondary. So if we have seen big transformer in terms of megavolt ampere and so on, this will be 1 volt ampere or maybe maximum 10 volt ampere. That's it, nothing more than that. It is going to be a very, very small sized transformer. It will still be iron core normally. It will be an iron core transformer, and generally gate has to get positive and cathode has to get negative when I am giving the gate pulses. So generally, if I say that this is my VCC, which is actually plus, obviously this corresponds to minus. So this will go to cathode, and in all probability I may put a diode as well to make sure that no negative pulses go into the gate, because it can be detrimental to the gate. So we will normally have a diode, and here is where I will have the gate connected. And here, when I am having the current during the pulse being in high stage, the current cannot be abruptly brought down to 0. So normally I may have a freewheeling diode here. There will be a freewheeling diode here, right? So much so for the triggering circuit of a thyristor or SCR. So you are starting from the pulses. You normally AND it with high frequency to make sure that the transformer which I am going to use here does not saturate, right? After high frequency ANDing, I necessarily need to amplify it, because in all probability SCR will require a higher current. So this amplification stage itself will have the pulse transformer connected in the collector of the transistor, so that I have complete isolation. Please note that this cathode, if I call it as the ground of the power circuit, here is the ground of the electronic circuit. This ground will be the same as that of the pulses ground and AND circuit ground and so on and so forth. So the electronic ground is here. So this is electronic ground. This is electronic ground, whereas this will be power ground. So the two grounds will be completely isolated from each other. And I am able to give this kind of an isolation with a transformer because it is an SCR. Once I give a pulse, it will start conducting. So even if I bring down, the voltage, still it will continue to conduct. It's not going to shy away from conducting. That is the major advantage of having an SCR, and we can have basically isolation with the help of a transformer, which we will see eventually that in BJTs or MOSFETs or IGBTs, we will not be able to do, because there, if you give a base pulse, the base pulse has to be in high condition continuously for the device to conduct. If the base pulse is not in high condition, it will come from on state to off state, and we don't want in all probability our device to go from on state to off state. Most of the times we fire it with multiple number of pulses, because by chance if it doesn't fire here, it can at least fire here. By chance if it misses these two, it can at least fire in the third, and so on. Okay? Because invariably SCRs are used with AC supply. And at what point really the alternating current goes from the positive half cycle to negative half cycle, or negative half cycle to positive half cycle, we may not be sure. So we want to make sure that we give it ample chance for conduction. That's the reason why we will repeatedly give the pulses, so that we give it ample chance to get into conduction. Right? So SCRs, if I look at, triggering is pretty simple. It's not too involved, because all you need is a high frequency ANDing and another amplifier and a pulse transformer, nothing more than that. But commutation is going to be a little more difficult, but before that we'll also look at series and parallel operation. I don't think I need to really expand upon that much, because we had already seen for diode. A similar situation happens for SCRs also. So series and parallel operation of SCR is very, very common. Very, very commonly we do the series and parallel operation. Yes. See, you are not doing the power amplification. This is even power amplifier. I should not say only current amplification. It is actually power amplifier. Because what I get from here may be 5 volts, and what I get from here may be 15 volts, and what I get from here may be milliamperes or microamperes, but what I get from here will be of the order of amperes. So I'm not only amplifying only the current, I'm also amplifying the overall power, and for that I'm drawing the power from VCC. So VCC is supplying the power for me to amplify the current pulse. Whereas in this case, if I just use a transformer, either you will amplify the voltage or you will amplify the current. You cannot amplify the power. The power is invariant, right, from the primary side to secondary side. So that's the reason why we use the transformer only for isolation, not for amplification. Right? Have I answered your question? See, basically it is not just the current alone. We say that gate has to be forward biased. So forward biasing voltage and the gate current, both will be specified for a device. In fact, if I look at the device specification, normally if I just say how the device specifications are given, normally what they will give is the forward blocking voltage, how much voltage it can block in the forward condition, right? The second thing they will give is what is the reverse breakdown voltage, right? And again, even in the reverse breakdown voltage, there will be 2 different kinds of categories they will give. Normal reverse breakdown voltage and repeated reverse breakdown voltage. If I just apply only 7 kilovolts, this device may be able to withstand. But if I repeatedly apply 7 kilovolts, it may conk out, because I am putting it under stress repeatedly. So it will conk out. So repeated reverse voltage and just once a reverse voltage or the peak reverse voltage that I can subject it to. So these are two categories normally they will give. Then apart from that, they'll also give what is IRMS it can withstand. Then they will give what is I peak it can withstand. Any device, right? And then they will say what is VGK that is needed for triggering the device. Then apart from that, they'll also say how much is IG, how much is the gate current that is needed. Then there is one more thing which will be coming out as turn on time. How long it takes for the device to come into on condition. After I give the gate pulse, does it immediately come on or does it take a little longer? So that is turn on time. Then there will also be turn off time, because turn off is not easy. We are going to look at that also, but turn off is going to be difficult. So which means if the recombination takes 50 microsecond, 100 microsecond, am I enabling the device to completely recombine? So that is essentially specifying what is the turn off time. Apart from that, they'll also give what is di by dt and dv by dt the device can withstand. How much is the di by dt the device can withstand? If I try to go beyond that, the device might break down. Similarly, dv by dt, because while turning on, I'm going to have from a large voltage, it will come down to 0 voltage or very low voltage. Similarly, when I'm turning off, it will go from a very small voltage suddenly to a large voltage, right? So in both the cases, it should be able to withstand. So dv by dt limits are generally given. And as we had done in series and parallel operation of the diode, here also I can have series operation of thyristor like this with large resistances in parallel. Similarly, parallel operation I can do for two thyristors with small resistances in series when I want to share a larger current I. Right? Here it is sharing a larger voltage V among the two devices. Right? Now this is very, very commonly used in high voltage DC transmission systems. I don't know whether you guys have heard of high voltage DC transmission system. In high voltage DC transmission system, what happens is, if I am having a generator, I'm just showing this as though it is a single phase generator. We call it a single line diagram. It is 3 phase, but I will show only one line at a time. Every line indicates 3 phases basically. So this is my generator, and I'm going to have basically a transformer which will step up. Maybe the generator will generate only 11 kilovolt or 12 kilovolt or whatever. From this, it is going to be generally stepped up to 400 kV. The transmission voltages are very, very large because we want to bring down the current. For the same power, we want to bring down the current. But the generator has a limitation of what is the maximum voltage it can withstand. Otherwise, you are going to have very thick insulation inside the machine. And in all probability, I will not be able to put such thick insulation inside the machine. That's the reason why we are having 11 kilovolts or smaller. Sometimes we will go up till 20 kilovolts, nothing more than that. So there is a limitation of generating voltages because of the insulation that is being used in the machine. Whereas the transmission voltages are generally chosen to be much higher because I would like to bring down the current. That is the reason. Right. So this has now brought down the current, and then from here it is going to go and it is going to get distributed, transmitted and distributed all over the country, for example. Right. But when I distribute it or transmit it, These are 3 conductors. Please note all these are at least 3 conductors. And apart from that, I may have a neutral also, because if it is actually the generator star connected, I may ground the neutral as well. So I will have 4 conductors coming out normally. So if I have 4 conductors coming out, and when I have 2000 kilometers being, spanned, maybe from northeast region to Gujarat. So obviously, I will have 4 conductors going all the way through these 2000 kilometers, which is definitely going to be extremely costly. So I can't afford to always have AC transmission. AC transmission comes in handy because of the transformer. It can step up and step down the voltages, which is very, very good. That's the reason why Tesla won the war of power, right? When you compare Edison and Tesla, Edison actually lost the war of electricity or power because he was always arguing for DC, whereas Tesla was arguing for AC, and Tesla was hired by Westinghouse, and Westinghouse is the one who ventured into AC transmission, right? So this AC transmission becomes costly when I am talking about long distances. So now that we have rectifiers and so on and so forth, everything is available with the power electronic converters. So what is being done normally is, whatever is available in the form of 3-phase, this is actually connected to a rectifier. And the rectifier obviously has to withstand 400 multiplied by √2 kV, because 400 kV is RMS. So 400 times √2, each of the devices have to withstand, and I have to put a factor of safety in all probability 1.25 or 1.2, so it is going to be way too high. There are no devices available for 400 kV multiplied by √2 multiplied by 1.2 or whatever. That's not going to be possible. So we use lot of thyristors in series. Normally that's what we do. So whenever I'm talking about this rectifier, this is going to essentially use large number of SCRs in series. This is going to have large number of SCRs in series. Now the rectifier has rectified the voltage, so I'm going to have a plus and I'm going to have a minus. Right? Now there are only 2 conductors. I can take it to extremely large distances. I'll save on copper. Instead of 4 conductors, R, Y, B and neutral, now I have 2 conductors. In fact, in some of the cases, this will be, return will be ground. In some cases, return may be ground, which means I have only 1 conductor, right? So compared to 4 conductors, if I can bring down the cost by using only 1 conductor, obviously it makes better sense. So that is the reason why many of the large distance transmissions now are being thought about to be done with HVDC, high voltage DC transmission. So high voltage DC transmission is applied in many of the cases where I have to transfer electricity over very, very long distances, so that I will be able to save on copper. That is one advantage. Another advantage is, let us say I have 50 hertz here. Maybe I want to tie it up to some other system which is having maybe 49 hertz on the other side. So I will have an inverter here. An inverter I can fire at my own will and wish. Not a problem. Fire it at 49 hertz. Ho gaya kaam. Right? So I can directly connect this to the 49 hertz source. And in between, of course, I may have several loads connected. Many loads may be connected directly to DC, maybe to AC, and so on and so forth. So high voltage DC transmission systems invariably use light activated SCRs. They use light activated SCRs because light, definitely is no way connected to electricity. I don't have to worry so much about isolation and so on. And it is a very, very high voltage and high power device. So inherently, if there is isolation, nothing like it. So I may use several LASCRs in series. I may not have to use them in parallel because I may have 400 kilovolts and maybe 4000 amperes. That is good enough, or 2000 amperes. And one SCR can carry very easily 2000 amperes, not a problem. So most of the times what we see in HVDC transmission system is series connected SCRs. Hardly ever we see parallel connected SCRs. So we'll have rectifier. For every device in the rectifier, there will be a string of SCRs, many of them connected in series. Of course, with parallel resistances, protection system. So the SCR may be only this much, but all the paraphernalia which is adding will be too big, generally, and the heat sink, and so on and so forth. So many things will be there. So this is typically the case when we talk about series operation and parallel operation of SCRs. Now let us go over to the commutation circuit. What we mean by commutation is to turn off an SCR circuit. How are we going to turn off a circuit? I'm going to take an example and explain it so that you'll be able to get an idea of how an SCR is turned off. So let us say I have a chopper circuit. Again, that is one of the simplest circuits, so I'm going to take a chopper. I'm having an SCR. I'm calling this as main SCR, M. Okay? And this is connected to the DC motor drive. Maybe I'm going to feed a DC motor drive with a chopper. The chopper consists of basically a switch, nothing more than that, right? A DC voltage source and a switch. Now I'm going to have a freewheeling diode. Of course, this we already said it is essential. If we don't have a freewheeling diode, it is going to be a problem because the current will be abruptly interrupted. L di by dt will be very large. Thyristor will conk out. So I don't want that to happen. And motor by default will have some inductance. Can't help it. So that's the reason why I'm putting a freewheeling diode. So this is a freewheeling diode. When I turn on this main thyristor or main SCR, I'm going to have the power supply given to my motor. But I would like to turn it off after some time so that the average voltage becomes less. I want to have a control over the voltage, right? That's why I am employing a switch. So I want probably this to be on for some time, off for some time, again on for some time, off for some time, and so on. This is how it is going to be. So this is T on and this is going to be T off. And this entire thing is going to be the period of the chopper, T. This is how it is going to be, right? So the average value of voltage, I told you already that whatever is the on time, correspondingly it is going to have T on divided by capital T, whatever is the period. So multiplied by the applied voltage. That is going to be the average voltage, right? This is how it is going to be. So I have to turn this off at this point. If I don't turn it off at this point, it is going to be difficult. I can't really get the average voltage to be less than whatever is the input voltage. So to turn it off, had it been a transistor or something, I could have just removed the base drive. If I remove the base drive, it will go off, simply. If it's a FET or whatever it is, the moment I remove the drive, it will go off. But in this case, it is not going to go off. We said that once those two transistors are driven into conduction, they will not come back. That's the problem. So for that, we have to have some auxiliary circuits which are known as commutation circuit. A typical commutation circuit I am going to show, right? So these are all part of commutation circuit, what I am showing in red. So many things. This is a capacitor, this is an auxiliary thyristor, then I'm going to have an inductor, I'm going to have a diode and so on and so forth. So many things are added to make sure that this particular device goes off. So whatever I have shown in red, the entire thing corresponds to commutation circuit. That corresponds to commutation circuit. So let me try to explain how this works. Okay?
So as I had told you earlier, the main thyristor M is actually going to give the power to the DC motor drive, and it has to be turned off at the end of T on. So if I talk about the entire thing as a chopper circuit which is feeding the DC motor drive, for T on it is going to be on, and for rest of the period it is going to be off. Again for T on it is going to be on, and so on. So this entire period is the period of the chopper. So 1 by T is equal to F, which is the frequency of the chopper. Okay. So I am going to have M fired at this point, and whenever I want to turn that M off, I am going to fire the auxiliary thyristor at this point. Okay. As I told you, all that is drawn in this red color, all these things are part of the commutation circuit. This is the capacitance C. Now let us say the capacitance is already pre-charged to a voltage like this. This could have been done by having an auxiliary resistor and a switch which can be closed for a short while until the capacitance charges to this plus and minus with VDC. The voltage is VDC currently. Okay. Now whenever I want to turn on turn off M, I am going to fire A. So the moment I fire A, there are two currents that will be flowing through M. One is directly from DC source through M to the DC motor. This is one of the currents, and the second current is going to be the capacitance itself is going to discharge. So you can look at the discharging path somewhat like this. This is going to be the discharging path. So I will have C, then M, then I am going to have the diode D1, then I am going to have inductance L back to C. So if I assume that L and C are ideal, it is going to have an oscillation, LC oscillation through this circuit. So if I try to look at the voltage, I am going to actually see that the voltage will reverse like this. It is starting from plus VDC and it will go to minus VDC. So this is essentially the capacitor voltage. So VC I am drawing like this. At the same time, if I try to look at the current would have reached the peak when the voltage is actually at the 0 point, and it is going to reach 0 when the voltage is at the negative peak point, that is when it is at negative peak. So this is going to be the capacitance current waveform, or is this the same as the diode current waveform. So this oscillation time will be equal to pi root LC. All of you know this definitely, right? In an LC circuit, pi root LC is going to be the half cycle time. So within pi root LC, this would have reversed its charge. So you would see that now this has become plus and this has become minus. The moment I am going to have this has become plus and this has become minus, now this is ready to commutate the main thyristor at any point in time. So I am going to now fire this auxiliary thyristor. So this is essentially when M is fired, whereas when A is fired after pi root LC elapsed from M, or even more than that, at that point I am going to have essentially the circuit somewhat like this. This is the capacitor which is having plus here and minus here, right? This is minus, and I am having the main thyristor here, and I have an auxiliary thyristor which is working like a short circuit. You can very clearly see that the plus is connected here and the minus is connected here, which is going to force a huge current in the opposite direction. The resistance is literally negligible because the current is having, a huge reverse component. right. So, essentially that cannot be allowed by the thyristor. So, M is going to go off. So, M goes off instantaneously. So, you can say because M goes off instantaneously, we call this as hard commutation. If you are allowing the reverse current to rise slowly, then you will call that as soft commutation. Soft commutation is such a case where you are going to make the reverse current rise slowly. If I allow reverse current to rise slowly, right. In that case, we will call it as soft commutation, but this is very clearly hard commutation. Once the commutation takes place, this M is not going to conduct anymore. When M is not conducting anymore, now the path for the current will be through the capacitance like this, through the auxiliary thyristor and through the freewheeling diode, through the DC motor drive like this. That will happen until the capacitance charges to plus and minus like this, fully to VDC, after which the capacitance will act like an open circuit. So, now the freewheeling diode will take place. I can actually say freewheeling diode should have been there in the circuit because DC motor has at least some amount of inductance. Now, you can see that the current will flow like this, it is just freewheeling. So, in this particular case, you can see there are totally 3 modes. One is first when M is fired to supply the motor drive. Simultaneously, you are going to have the capacitance reversing its charge, okay, which means this will need at least pi root LC as the time that is needed for the main thyristor to be on. So, this is the minimum on time. I cannot have less on time than this. This is the minimum on time. The second portion is when M has to be commutated or turned off. Under that condition, I am essentially going to fire A. When A is fired, I am going to have essentially instantaneously, right, instantly I am going to have M is turned off because of very high current flowing in the opposite direction. And after this, I am going to see that auxiliary thyristor, that is the auxiliary SCR, allows capacitance to be charged back to VDC. So, it will be ready for the next cycle of operation. After this, freewheeling diode takes over. So, basically this circuit is designed based on 2 things. One is this minimum T on, which is pi root LC. Another one is you are going to have basically I load or I armature of the DC motor might have been given already. This is the load condition. So, you can say C delta V equal to I delta T, right. And if I actually look at it, the capacitance voltage is literally going from plus VDC to 0 to minus VDC. This is how it is transferring, right. So, which means whenever it is actually having the voltage with the polarity plus here and minus here, then this main thyristor is going to be reverse biased. Only if it is reverse biased, it is going to be turned off properly. So, how long will it be reverse biased? Until this voltage becomes 0. So, I can say delta V in this case happens to be VDC, C is the capacitance value, and I am going to have I as the armature current, whatever is the armature current multiplied by delta T. So, how long does it take to reverse is governed by the capacitance, what is the DC voltage and what is the load current. This delta T has to be greater than the turn off time, which is the recombination time for the charge carriers to recombine. So, this turn off time, it has to be greater than the turn off time of the SCR, which is specified in the data sheet. This will be specified normally in the data sheet. So, you usually need two conditions. One condition has to be this delta T constraint, the other condition is pi root LC constraint. These two together you should be able to design this entire L, C and so on. Okay. So, this is a typical commutation circuit which is used for turning off an SCR. So, you know that to turn off an SCR is not an easy task. You will require a major auxiliary circuit for this. That is one reason why in DC AC inverter circuits as well as DC DC chopper circuits, generally SCRs are not commonly used because input excitation is DC. So, never are you going to reverse bias the SCRs very easily, naturally. So, SCRs are not used commonly in these two circuits because it is not going to be easy to turn them off. Whereas, if it is AC DC circuit and so on, automatically voltage will reverse, the source voltage will reverse, because of which commutation or natural turn off or natural commutation will take place, right. So, it is always good to use SCR in AC excited circuit, not good to use them in DC excited circuit. So, if we summarize, the turning on of the SCR mainly requires a few conditions to be followed. First, the device has to be forward biased, which means I am going to have V at anode is going to be greater than V at cathode. Voltage at cathode will be less than voltage at anode. The second condition is gate pulse should be given, which means gate terminal is at a higher potential. This potential will be higher as compared to cathode potential. Okay. The third condition is even after these are done, the current, that is the current flowing through the device has to be greater than the latching current of the device. The latching current essentially gets that name because the device will be latched into conduction only if the current is greater than the latching current. These are the three conditions for the turn on of the SCR. For turning off the SCR, at least two conditions have to be followed. The first condition is the current through the device, that is the anode current I am talking about, has to be less than the holding current. If I say latching current is somewhere around 10 milliampere, holding current will be somewhere around 9 milliampere. They will be very close to each other, there will be hardly any difference. But the anode current first of all has to be decreased to a value which is less than the holding current. Please note that is what happens in this commutation circuit case. Originally the current that was flowing was the load current. Now whatever is the current that is flowing in the reverse direction is the surge current due to the capacitor. This is I surge basically, right. This is going to be I surge. So, this I surge will be definitely higher than I load. So, overall current becomes negative. So, the first condition to be followed is the current has to be less than the holding current, maybe negative direction. The second condition is after the current decreases, right, we have to reverse bias. The device has to be reverse biased at least for turn off time. So, at least for TQ. TQ is the turn off time of the device specified in the data sheet. Turn off time of the device which is specified in the data sheet. Okay. So, these so much so for SCRs. Now, we have still not talked about protection of SCR. So, SCRs are generally slower devices, so it should not be too difficult to protect them. Against overcurrent, if you want to protect them, normally semiconductor fuses are used. Semiconductor fuses will be melting before the device conks out. So, I square T rating of the fuse basically has to be smaller as compared to I square T rating of the device. What I mean is the heat generated in the fuse will melt it much more as compared to whatever is the heat generated actually in the device. So, the device will not conk out. The second thing is di by dt protection. Di by dt protection is generally done by having a series inductor. The inductor will never allow the current to rise right away. So, normally if this is my device, in series with that I will put a small inductance. So, this will make sure that the current does not increase untowardly. The third one is dV by dt protection. If the dV by dt goes beyond a particular value, if dV by dt is greater than whatever is the allowable dV by dt of the device, then the device can turn on. So, the turn on can happen even due to this. After all, when you apply a large rate of rise of voltage, C dV by dt is generally I. So, any junction capacitance can be represented by the C. So, if by chance dV by dt is much larger, the current that is passing through any of the junctions can go way beyond the limit, which will automatically make the device on. So, you do not want spurious turn on of the device. That is the reason why dV by dt has to be within the limit. So, generally RC snubbers are used for protecting the devices against spurious dV by dt turn off. Let us take a typical circuit. Let us say I have probably voltage source, maybe 100 volts or something. Let us say I have a 20 ohm resistance, right, and I am going to have a thyristor here, okay, and it is going to be turned on and off. I am not really showing the gating circuit or I am not showing the commutation circuit. When this is turned off, entire 100 volts will come across the SCR. So, if I try to look at the voltage, this will be plus and minus, and 100 volts will come across the device if the current is going to be 0. If I is flowing, then there is no problem. If I is equal to 0, I will get the entire 100 volts right away. This can actually turn on the device, spuriously. It will not go off at all. Just to prevent this, what I can do is to connect an RC circuit. Normally, a diode is also connected here. When a diode is also connected, it is called polarized snubber. So, during this condition, what happens is, I am going to have essentially this 5 ampere flowing through the diode to charge the capacitance. So, the capacitance is going to get charged with plus here and minus at the bottom, right. So, this is R, this is C, but R does not have any role to play right now. So, I am going to have C times dV by dt, whatever can be withstood by my thyristor, equal to I, which is actually 100 volts by 20 ampere, which is 5 ampere. Let us say this dV by dt, which can be withstood by the device, is 200 volts per microsecond. I am just arbitrarily taking the value. So, I will have C equal to 5 ampere divided by 200 into 10 power 6. So, I am going to have essentially 5 divided by 2 is 2.5. So, I am going to have 2.5 multiplied by this is 10 power minus 8 farads. So, that means 0.0025 microfarad, that is what I am going to get. So, if I choose a capacitance which is of the order of this particular capacitance value, I will make sure that the voltage across the SCR is not exceeding the dV by dt limit that is given by the data sheet. So, RC snubber or polarized snubber helps me to make sure that the capacitance is not gaining a voltage at a very fast rate. The capacitance is right across my thyristor. So, the thyristor will also not have a huge dV by dt. But what is the role of this resistance? That is what we will have to check also. I have turned off the SCR. Now, if I am going to turn on the SCR, please note the capacitance will try to discharge through the SCR. If I do not have a resistance, the current that will be flowing through the SCR, although it is in the correct direction, it is flowing from anode to cathode, this is going to exceed the limit. The I value will become extremely high. So, discharging current during turn on, right, that is limited. This is limited by R. So, I have the function of diode spelt out, I have the function of R spelt out and capacitance spelt out. So, this is essentially talking about RC snubber, right. So, with this we are kind of concluding our discussion on SCR. Now, the next device which is related to SCR which I want to take up is TRIAC. TRIAC is basically a 5-layer device and it is equivalent to a back-to-back connected thyristor or SCR pair. What I mean by back-to-back connected SCR pair is, I will have one thyristor connected like this, another thyristor connected like this, and they are connected in anti-parallel. So, TRIAC is exactly equivalent to this. Let me draw the symbol of TRIAC. The TRIAC symbol is somewhat like this. I am going to have one triangle like this, one more triangle like this, and I am going to have a gate terminal. So, one of them is specified as MT1, the other one is specified as MT2. There is no point in telling this as anode and cathode because the current can either flow this way or flow this way. So, there is no point in telling that this is the gate terminal. So, this is the symbol of TRIAC. This is going to be the symbol of TRIAC. The TRIAC is a 5-layer device I told you. So, we are going to have something like P, N and P. These are the 3 layers. Then I am going to have a N plus here and I am going to have one more N plus here. Okay. Now, my gate may be connected basically from here. This is the gate terminal. Let me call this terminal as MT2 and let me call this terminal as MT1. So, these are the 3 terminals that are available and TRIAC can be fired by having MT1 with respect to MT2 as positive and simultaneously gate is also negative with respect to MT2. Okay? Or I can also have MT1 with respect to MT2 as negative, which means MT2 is positive. At that point, gate is also positive with respect to MT2. So, I can have essentially any of them. So, gate can be positive pulse or negative pulse and it is always measured, let us say, with respect to MT2 and I am going to have essentially the TRIAC being fired in either direction. So, we are going to see that normally the TRIAC is going to be used in, you must have seen fan regulators, electronic fan regulators. So, in that TRIAC is very commonly used. So, if you look at the electronic fan regulator, what we apply is a single phase voltage like this, and we are going to apply the voltage only for a short while like this. So, which means I will fire probably during the positive half cycle at some alpha and during the negative half cycle at some other alpha, which is pi plus alpha. So, I would see that normally the RMS value of the voltage is going to be controlled by either advancing this or retarding this. So, I will be able to control the RMS value of voltage and hence the speed. It is also used in dimming the lamps, either it is at home or stadiums and so on. In those cases, the triac is very commonly used for AC voltage control. So, let me probably conclude the thyristor topic by getting into what is known as a GTO. GTO stands for gate turn off thyristor. Okay. So, what we saw in the case of a normal SCR is turn off is very difficult, turn off is not easy, whereas in gate turn off thyristor we will be able to turn it off by applying a negative current, but this negative current will be a large current in the gate terminal. So, by applying a positive current in the gate terminal, which is a small current, we are going to turn on, whereas in GTO we will be able to turn it off by applying a large negative gate current. The GTO symbol is somewhat like this. I am going to have essentially this is the normal SCR symbol we see, but here the gate is going to have, one is going to show the current inward, the other one is going to show the current outward, and this is the gate, this is the anode and this is the cathode. This is how the symbol is normally, which indicates that the current can go out or go in to the gate terminal. Okay. The GTO actually looks somewhat like this. If I am going to see basically that this is PNP, I am going to have actually a N which is highly doped, and this is going to be actually my cathode, and this is going to be my anode, and this is going to be the gate. So, in this gate I have to make sure that the current can go in either direction. Normally when the thyristor is conducting, you are going to see that lots of holes are going to be here. Essentially by applying a negative current, you are going to evacuate all that hole. So, from the anode and gate regions, the carriers, charge carriers are evacuated by applying a negative current. One major problem we face with GTO is that we normally see that even after turn on in SCR, there is no need to retain the positive gate current, right. Once you give the gate current, it will just remain on, right. After that you do not need to give the gate current, but in GTO for better reliability, if I want to have a better reliability, at least a small gate current, a small positive gate current has to be retained. This is one problem. Whereas, one more problem is in SCRs, normally you would see, if I look at I anode divided by I gate, this is of the order of 1000. the current amplification is really good in the case of SCR. Whereas in GTO, in the positive side, I would say I will have a current gain of 1000 approximately, which is I anode by Ig. Whereas if I look at the negative side, that is the turn off side, I am going to have I anode by Ig magnitude. I am talking about magnitude because it is negative current, will be only of the order of 5 or 6, nothing better than that. So, for example, if it is a 1000 ampere GTO, 1000 ampere rated GTO, I am going to require turn on current, gate current, right, is going to be only of the order of 1 ampere, whereas turn off gate current is going to be of the order of almost 200 amperes. So, you can imagine this 200 ampere is way too high. So, gate design, gate circuit design is going to get very complicated compared to an SCR. But the flip side of it or positive side of it is we would be able to operate at a much higher frequency. So, if I say that normally thyristors work only around 100 hertz, that is the normal operating frequency of an SCR, GTO can easily operate until 1 kilohertz, because normally if I compare the turn off time of an SCR, this will be almost 10 times the turn off time of a GTO. So, the operating frequency can increase tenfold. This is the advantage of GTO, right. But there are some new devices that have been designed by Mitsubishi and GE, which is known as integrated gate commutated thyristor, which is actually able to have an amplifier in the gate circuit. There is an amplifier in the gate circuit. This is a built-in amplifier. So, you can have lower current for turn off as well, and it is able to work very well. So, this is really becoming popular. This combines the advantages of SCR as well as GTO by including an amplifier in the gate driver. Okay. Now, we are now slowly moving to the transistors. So, let us start now with power BJTs. So far whatever we discussed, they were all coming under the category of thyristor. Initially we talked about diodes, then we talked about thyristor, right. Now we are coming to this bipolar junction transistor. This is exactly similar to the electronic transistor, but only thing is that most of the times we use only NPN, not PNP, because in this case majority carriers are going to be electrons, and electron mobility is generally better than hole mobility, and we are looking at very large current. So, that is the reason why generally we go for NPN and not for PNP. And normally we look at this in common emitter configuration, where I am going to give a base drive, and normally you must have known that transistors have 3 regions of operation. One is going to be cut off. Let me just draw how the transistor characteristics are. IC is plotted with respect to VCE. This is how the transistor characteristics are. So, I will have maybe for a particular gate current, this is how it is, another gate current it is going to be like this, another gate current it is going to be like this, and so on. This is how it is. So, let me call this as maybe IB1, this is corresponding to IB2, this is corresponding to IB3, and so on. Very clearly the collector current is increasing as the current is moving from IB1 to IB4. So, I would have IB1 as the least, IB2, then IB3 and IB4. If you look at this, there are distinctly 3 regions of operation. This is the cutoff region, this is the saturation region where VCE is almost a constant, and this is going to be the active region. Wherever I have written here, this is going to be the active region. In active region, neither VCE is very small nor ICE is very small. So, generally in active region, we see that device dissipation is large. If the device dissipation is large, that means I have to have a very large heat sink to actually dissipate that heat. So, it is not a good idea to operate this in the active region. If I want very high heat sink, big heat sink, then it is going to increase the weight of the converter also. So, normally this active region is only used when the transistor is used as an amplifier, which is normally analog electronic circuit application. Whereas, in power electronics, I am either going to operate it in cutoff region or going to operate it in saturation region. So, whenever it is operating in cutoff region, it will be in off condition, and whenever it is going to operate in saturation region, it will be in on condition. So, I am going to operate the transistor only as a switch. So, I am essentially turning on and turning off depending upon how much is the gate current that I am giving. So, transistor happens to be a current driven device or current controlled device. So, what I would see is, if this is my NPN transistor symbol, I am going to give a particular value of IB. This is probably grounded, and what I am taking from here is IC, and what I am applying here is VCC through a resistance, right. If the device is in saturation, I am normally going to get IC divided by IB, which is beta, that will be only anywhere between 10 to 12. So, if it is a 100 ampere transistor device, I will require almost IB equal to 10 ampere. This 100 ampere obviously specifies IC. So, IB has to be 10 ampere, because of which the base drive circuit power capacity is quite high. If this is quite high, I am going to definitely have the design is not simple. This is one of the major problems of this transistor. Because the base drive design is not simple, not much of research has taken place in the transistor. That is why the ratings are still limited. You have the transistor ratings only of the order of hundreds of kilowatt at the most, nothing more than that. Whereas in thyristor, I had already told you that almost 30 megawatt one single SCR can handle, whereas hundreds of kilowatt only one particular BJT can handle. It is not really good, in terms of the power capacity. And if I actually look at the normal transfer characteristics of the transistor, I am going to have VCE on one side and IC on the other side. So, I am normally going to see that VCE is actually equal to VCC itself when the device is in cutoff region. So, this is the cutoff region, right. Whereas, I am going to see that I am going to have slowly the reduction in VCC, and it is going to come to a minimum value. So, this actually is going to be corresponding to VCE equal to 0.7 volts approximately, which is actually VCE saturation, right? And this is essentially the saturation region of the transistor. Obviously, whatever is in the middle is the active region. Okay? This is generally known as the transfer characteristics of the transistor BJT, right. So, under this condition, we can very clearly say that the active region is hardly ever traversed by any of the power BJTs. Either I am going from off condition to on condition, which is saturation condition, or from saturation condition to off condition. Only during that time this active region is going to be traversed. Otherwise, never do we operate in active region as far as my BJT is concerned. But if I try to look at the normal operation of the transistor, I can say probably this is IC and this is VCE. I am probably going to have for a rated IC, right, I am probably going to have very small VCE. So, VCE times IC is going to be the dissipation inside the device. Because please note, VCE is the voltage across the device between collector and emitter, and IC is the current carried by the device. So, the product of these two is the dissipation inside the device. As our IC decreases, VCE will increase. So, I may have something like this, and then again I am going to have probably some portion where I am going to have VCE to be very small, but IC to be very large. So, I would call this as the safe operating area for the transistor, which means within this region I am going to have the heat dissipated, whatever is the heat dissipated within the device, it can be easily shunted out. But if I try to actually load it more than this current or go for a higher voltage, I am going to have a big problem. So, this is for continuous or DC operation. But if I am going to have it in pulsed operation, for some time I am going to turn it on and sometime I am going to turn it off, then probably I can increase the limit slightly. So, this is essentially corresponding to pulsed operation. So, if I am going to have some pulses only, then I would be able to dissipate more heat because every now and then my device gets some rest. So, in general, whenever we design a transistor circuit, we have to check whether it is within safe operating area of the device or not. That is what is going to actually tell us whether I will be able to operate it safely, right. So far we have seen at least the transistor structure. Oh, I forgot to draw the transistor structure. So, I should say generally in transistor structure what happens is I am going to have an N substrate inside which I am going to have N plus doping, quite a lot of doping. So, this will correspond to the emitter, right. Then I am going to have the P which will be corresponding to the base. So, this will be corresponding to base. So, this is essentially my base terminal which is very thin. Normally, this is going to be thin. Okay. Then after that I am going to have one more N inside which I am going to have again N plus, that is heavy doping. So, this particular portion is going to correspond to the collector. Normally, we call this region as the drift region. This drift region is going to offer some amount of resistance. The longer the drift region, the resistance will be somewhat larger. So, we had seen so far basic structure of the transistor, we have seen the transfer characteristics, we have seen why the base drive requirement is somewhat higher and what are the three regions of operation. We had also looked at what is the safe operating area of the device. In the next class, we will be looking at the series and parallel operation. We will also be looking at the protection for the BJT, power BJT. Thank you.